Number 7! Scared you, didn't I? All right. This is a weight suspended from a spring. The variation with weight of the length of the spring is shown below. So, first of all, when I see length and weight, that right there, to me, is already the giveaway that we're dealing with a spring. Weight and length. Now I'll tell you, here's the thing though, let's be careful about this. There's actually a little situation here. So picture a spring, okay, and then we'll put a little weight on it, like this. And then here's what I want to say. The spring without the weight probably looks more like this. Hopefully I can draw this. So here's the spring. And then we'll say without the weight on it, it kind of compresses a little bit like that. Oh my goodness, the power of computer graphics. Look at that. So what we're saying is that we stretch from here down to here. And that's like the length L. And then when we draw a free body diagram here, we're going to actually have an upward force from the spring and a downward force from the weight. And we're saying that these balance. So it turns out that mg, the weight, equals k times the length of the spring. Now, since we're plotting x and weight, let's be clear, when we rearrange, this is going to be 1 over k. So this is on the x-axis. This is on the y-axis. And this is the gradient. So when we actually get the slope here for the spring constant, I'm just going to first calculate the gradient here. So that's going to be 14 minus 12 over 4 minus 0. That's going to be 2 over 4, which is 0.5. And the units on that are going to be centimeters per Newton. But the thing is, we need our unit. So this is actually calculated as 1 over k as 0.5. So when I actually get k, I need to actually take the reciprocal of this, and that's going to be choice C, 2 newtons per centimeter. Very exciting stuff. So we'll move on to number 8 in a second. Now for number 8. Which one of the following objects is trapped in equilibrium? Let's see. Okay. This one here. This is one of those famous stone trapped in the tread of a rotating tire. There, you're going to have, I'm going to call it like a gripping force that pulls the stone up and keeps it going in a circle. Air molecule, as a sound wave passes through air, that's going to be vibrating back and forth. A steel ball falling through constant speed through oil. There's your key, constant speed, and in a straight line. So the situation here is that we have mg pulling it down, and then we have a drag force pulling it up. So choice C is absolutely the correct choice. And then choice D, an electron moving through a metal under an action potential difference. Just please keep in mind, on these problems, there's always going to be these weird choices. Where your thought is, where's the formula? What's going on here? I don't get it. So do expect that on these problems, but also know that buried in these choices is going to be something that we have studied that's really going to be clear that that's the choice that they want. So that's questions 7 and 8.